Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. Module 43. Today we will present a proof of Brouwer's fixed point theorem, which you may term as analytic proof. There are quite a few different proofs of this one, and this is due to Milnor. You may have come across with the following classical and famous result, which we call Brouwer's fixed point theorem. Every continuous function from a closed disk Dn to Dn has a fixed point. Certainly for n equal to 1, if you take the closed interval -1 plus 1, it's a familiar result to you in the real analysis course. Indeed, it is an easy corollary to intermediate value theorem. Right? Maybe you have done it any closed interval AB to AB, you have a function, continuous function, then it has a fixed point. The general version was proved by Brouwer using Lebesgue covering theory. In modern times, it is fashionable to prove this using homology theory. You may find a proof of this using simplicial approximation in my book, for example, or in NPTEL course on Algebraic Topology Part-I. Milnor gave a proof of this using just multivariable calculus and Stone-Weierstrass theorem. In fact, Stone-Weierstrass theorem for functions defined on a closed and bounded subset of Rn is much easier than the general Stone-Weierstrass theorem. So, in this section right now we will present a proof which is simplified version of Milnor's proof, and that is due to C.A. Rogers. In Hurwitz and Wallmann's book, which I am referring quite often, the authors also give a completely elementary proof, quote unquote, of the Brouwer fixed point theorem. However, the word elementary should not be confused to mean easy. Indeed, the concept they introduce in order to prove this theorem, namely triangulation, they don't use the word triangulation at all, but that is what they are doing, and that is in an ad hoc manner they are doing. So that is better left to be learned properly in an algebraic topology course. So that is one reason which we are not very keen to present that proof here. On the way, while learning Milnor's proof, you would have witnessed, inverse function theorem and Stone-Weierstrass theorem being applied. So that is also another motivation. So both of these things we have studied in this course itself. So the main reason to include this result, which is seemingly a diversion, is that it is going to play a key role in the final step of our goal in dimension theory. Okay, so that is why it is here. So let us begin with Ernest this lemma, which gives you three equivalent conditions. All of them are the statement of, not a conclusion, statement of Brouwer's fixed-point theorem. Every continuous respectively C1 function from f from Dn to Dn has a fixed point. There is no continuous or respectively C1 function R from Dn to Sn minus 1. So the codomain has changed here. Pay attention to that, such that R of x equal to x for all x inside Sn minus 1, that is the boundary of Dn. So such a map R is called a retraction of Dn on to Sn minus 1. We don't need that word, but just for your information I am telling you that. The third condition is there is no continuous respectively C1 function h from Sn minus 1 cross I to Sn minus 1 such that h of x0 is x and h of x1 is x0, a constant for all x in Sn minus 1. The third condition just says that the identity map of Sn minus 1 is not homotopic to the constant function. There is no continuous means not homotopic to constant function. So in each of them I have put in the bracket this C1, C1, C1. So there are one version which is all where you have to take C1 all everywhere, another version which you have to take just continuous. That is the meaning of this. These three are equivalent conditions. Notice that B and C are statements in negation, whereas A is an assertion. So that is the beauty of this approach here. So what we will do is we will prove that these three conditions are equivalent. Okay. Then in order to prove this one, we can either prove this or prove this one. So that is the whole idea. Okay. So let us prove that A implies B. Everywhere I am now going to take only continuous function, then I will indicate what to do when you have C1 function. Okay. So assume that every continuous function from Dn to Dn has a fixed point. Now in order to prove B is not true implies A is not true. That is what we would like to prove. A implies B. Okay. If B is not true, B itself is in a negation, that means we have a retraction, namely continuous function from Dn to Sn minus 1, which is identity on the boundary, right? Take that map, compose it with this alpha which sends x to minus x, antipodal map. Okay. So you are inside Sn minus 1. Now you go back to Dn by the inclusion map. That's all. Okay, what happens? This function will never have any fixed points at all. Okay. See, if this whole thing is f, fx is equal to x, first of all, means that the point x has to be on the boundary, because fx will be in the boundary here, Sn minus 1. But on the boundary, this is identity followed by x going to minus x. So identity x goes to minus x here. Okay. So fx cannot be minus x. Okay. Fx cannot be equal to x. So that's all. So there are no fixed points for this composite function. So that's a contradiction, that is denying A. So that means not B implies not A, which is same thing as A implies B. Now I want to prove B implies A. Suppose there is a map f from Dn to Dn such that fx is never equal to x. Extend the unique line segment fx to x. See, these are vectors inside some Rn. So line segment between 2 points makes sense, 2 vectors makes sense, fx to x. But you take this line segment, extend it in the direction of fx, okay, from fx to x, from fx to x, okay, so that whatever point you get, it should be on the sphere, okay, so you will get a unique point. So why this makes sense? Because the entire line segment is contained in the closed unit disk. Maybe it is inside, strictly inside the unit disk, so you will have to extend it. Okay, as soon as you extend it, because the boundary, because the entire thing is a bounded set, it will have to hit the boundary somewhere. Okay, so hit boundary is a sphere. So this is just a geometric way of getting this function g. In olden days, that was enough for people to understand that g is continuous. Even today, I can leave it as an exercise. But here, because you may be seeing such things first time, I will give you a full proof of why gx is continuous, just because this f is continuous, fx is continuous. Okay. So how does it do that? Look at the entire line segment, entire line from passing through x and fx. Okay. So what is the parameterization? It is t times fx plus 1 minus t times x as t ranges over R, right? So this left hand side, this right hand side as t ranges over R, they are all points inside this line. Now we want this line to be one on the sphere and from x to fx, so fx to x, so it is towards x. Okay, so beyond x, maybe it's x, but it's beyond x, including x. Therefore, I have to take the non-positive root of the quadratic equation. Why quadratic equation? Norm of the right hand side must be equal to 1. Norm square equal to 1 will give you quadratic equation. So norm square, when you write, I am rewriting it this way: t square times norm v square plus twice t into v, this is the dot product v dot x, plus norm x square minus 1 equal to 0, where v is a short form for fx minus x, the vector fx minus x. You can just check that when you take norm of this function here, write it into fx minus x, t times this and so on, what you get is this one. Here t is the variable, x is fixed, therefore fx is fixed, therefore v is fixed. So this is a quadratic with some coefficient, norm v square twice v dot x, and the constant term is norm x square minus 1. Okay. Now, where does x range? X is inside the closed ball, okay, Dn. Therefore, norm x square is less than equal to 1. So norm x square minus 1 is less than equal to 0. This is a negative thing. It follows that the discriminant of this quadratic, okay, is non-negative, okay, and identically 0 if and only if this norm x square is equal to 1. Okay, not only that, identically 0 means the other one, this coefficient v dot x must be also 0. V dot x is 0 means what? X and v are perpendicular to each other. So therefore, what we happens is norm of fx square will become norm of x square plus norm of v square. Okay, norm of x square plus norm of v square, okay, which is bigger than 1, which is absurd. All right. So therefore the discriminant is strictly positive, and hence the two roots are continuous. Okay, so what I am saying, discriminant is non-negative, identically 0 if and only if this happens. Okay, if this happens there will be a problem, so it must be strictly positive. That means we have got the two roots are continuous functions. Okay, whenever something is 0, when the roots are equal and so on, there will be problem about continuity, which root are you choosing and so on. So here the discriminant is strictly positive, so there is no problem about that. So continuity of the roots follows. What we have to take? We have to take the non-positive root of this, and that will give you the solution, which is a continuous solution. So G will be in terms of that, because put that value t, okay, then left hand side, this right hand side will be G of x. So here is a picture of, and proof is completed for many people. Fx is here, x is here. I am extending it towards x, from fx to x, and hit G. By chance, if x is already on the boundary, then gx is equal to x. So that is the beauty of this construction. Okay, G is like R in our statement. Okay, that is the whole idea. Okay, so we have completed the proofs of A implies B and B implies A. So here again what we have proved? Not B implies not A. No, suppose there is a map like this. No, not A. So not A implies not B. Earlier, not B implies not A. Not A implies not B. That is what we have proved. Now B and C are very easy. Look at this formula. R times R of 1 minus t times x equal to h of xt, where x is on Sn minus 1, t is between 0 and 1. So 1 minus t is also between 0 and 1. So this is an element of the closed disk. X is an element of the boundary sphere. Okay, R times this one will make sense for all functions defined on Dn. Okay, I am just putting h of xt. If I know h of xt, I could have defined R by this formula and vice versa. So this is the formula which will define either side if you know the other side. If R is given as in B, when hx is continuous, R will be continuous. Okay, and if h of x comma 0 is x, then this just means that R of x is x. That's what we wanted, that it is a retraction. Okay, h is of course taking values in Sn minus 1, therefore R will always take in Sn minus 1, right, and vice versa. And finally what happens when t equal to 0? Okay, h of x, when t equal to 1, h of xt is a constant. And what is that constant? R of this one, right? So that if you have R, then h will satisfy that property and vice versa. Okay, therefore this one formula proves both B implies C and C implies B. Now comes the part wherein we take everywhere C1 functions. Okay, if this is C1, then that is C1 and vice versa. So there is no problem when B implies C. In here what happens? If all these functions, namely fx is a C1 function, these roots are also C1 functions. In fact, they are analytic functions. Right? Roots of a polynomial, wherever they are positively defined, strictly defined, they are analytic functions. All right. So that will take care of that. Wherever I have, so here also alpha is also a smooth function, x going to minus x. So this is an inclusion map. So if this is C1, the composite is C1. So what we get, f piece will be C1 and so on. Okay. So simultaneously, all these three statements in both C1 case as well as general continuous case are proved. By the way, even if you just prove C1 case here, you have to argue for continuous separately. These have to be done separately. There is no other choice here. One doesn't imply the other. You have to go through the whole thing separately, but that's easy anyway. So having prepared the ground for the general theorem now, the idea is to prove the smooth version of B and then use Stone-Weierstrass to prove the continuous version of A. You see, both 6-point theorem we will prove like that. We state and prove these two things separately, no confusion. Okay. So there is no C1 function R dn to Sn minus 1 such that Rs equal to x for all x belong to Sn minus 1. Now this is an assertion. Earlier this was just a statement equivalent to two other statements. Now we are proving this one. Okay. So what is the proof? Assuming that there is such a function, let us just tentatively put Sx equal to Rx minus x, and for each t in 0, 1, let us put Rt of x equal to 1 minus t times x plus t times Rx. So joining the identity map and Rx, this can be rewritten as x minus tx you combine with Rx and write it as t times Sx, because Sx is Rx minus x. Okay. Just look at this formula. Rt is from dn to dn, because Rx is from dn to Sn minus 1, x is identity, and this is line joining the 2 points, you see. So it will be convexity of dn will tell you that this is always inside dn. However, this difference may go out also, you don't know where it is. So this S is from dn to Rn. Because I started with R as a smooth function, all these are smooth functions. Now let us have a notation here. Bn denote the open disk, namely set of all points wherein norm x is less than 1. For each fixed x inside Bn, take the total derivative of Rt. Okay, that's a linear map from Rn to Rn. Okay, that's the total derivative. Okay, note that the total derivative of Rt at any point is the identity map of Rn plus t times the derivative of S operative on x. Okay, this is also a linear map from Rn to Rn. So d of Rt is identity plus t times d of S. So these derivatives are taken with respect to x. Okay, t is also variable. You may wonder what is happening. Rt, where t is frozen here, you see. Rt is one single map. For each fixed x, now you look at the function t going to the determinant of this linear map. See, this is a linear map from Rn to Rn, right? So you can talk about its determinant d of Rt at x. Okay, x is fixed now. One linear map is there. look at the determinant, but t is there, so determinant of this identity plus some matrix, it will be a polynomial in t of maybe possibly of degree n, right? So t occurs in each entry here. Okay, so this is a polynomial function. Therefore, if I define the function f from closed interval 0 1 to r by taking the integral of this function, determinant of d t r t, okay, integrated on the entire of this open ball Bn. Okay, remember that this function is a continuous function. Okay, because we started the c1 function and then we have taken one's derivative. So derivative is a continuous function. So this is just a ordinary Riemann integration. Okay, n-fold iterated integral, you may say. Okay, so there is a variable t involved here. Therefore, this will become a polynomial in t, polynomial function in t, because integrated integrand is a polynomial. Okay, this polynomial we are going to show that it's a constant function. What is that? Integral ft is a constant function. Then we will compute f0 and f1 separately and show that they are unequal. That is a contradiction. We started with something, in the contrary, there is no function is a statement, assume there is a function, so we are getting a contradiction. That will complete the proof. So what does it remain? We have to compute f0 and f1. Okay. So first claim is there exists 0 less than t0 less than 1, okay, such that this RT is injective for all t between 0 and t0. Okay, look at 0, you have no control. Now, what is R0? R0 is just x. There you are lucky, it is injective. Okay, so we now say that there is some positive, there is an interval of positive length here in which RT is injective. Okay, look at the function s from Dn to Rn. This is a C1 map, right? Therefore, there is a constant C positive such that this Lifshitz condition holds. Sx1 minus Sx2, the norm is less than some constant times x1 minus x2 norm. Okay, this is true because Dn is compact, closed and bounded, and C1. So you look at the derivative, take the maximum of the derivative, that can be taken as C. That is the general statement here. This is some calculus. Now suppose x1 is not equal to x2 and RT of x1 equal to RT of x2. Remember, we have this formula, right? RT is x plus t times Sx. Now that will imply that x2 minus x1 is equal to t times Sx1 minus Sx2. Okay, because RT of x1 is equal to RT of x2. So you put equality, you get this one. But then norm of x2 minus x1 will be less than t times norm of this. Okay, t is some positive constant 0 to 1, right? Norm of this, norm of that is less than c times norm of x1 minus x2. all right. But then these two numbers are the same here, and they are x1 is not equal to x2. This is a non-zero number. The non-zero number is less than or equal to some number times the same number, means this must be bigger than 1. Okay, once it's bigger than 1, I can choose 1 by c as t naught, and then for t less than t naught, we will never have this. That's all. Okay, so this can happen only beyond this t naught. That's why we take something less than or equal to t naught. This will never happen. That means that S is injective. The RT is injective. Sorry. All right. Now let us go ahead. Okay, as before, Bn denotes the open unit ball inside Rn. We claim that there exists a T1 now, another constant, between 0 and open 0 this time. Again, positive constant I want. Less than or equal to T naught. We don't want to go out of T naught. Such that this function Rt from Bn to Bn on the open disk is a diffeomorphism for all t belonging to 0 T1. So this is a claim now. There is such a t. It may not happen for all of them. Okay. If this T1 is larger than T naught, we will take a smaller than that. Once it is true for all that, then you can take let T naught, you can take T1 equal to T naught itself. That's all. That is not a big problem. So we have to find such a T1. That is the whole idea, which is positive. Now look at dr of x, which we have seen that identity of Rn plus t times ds of x, right? Therefore, it follows that there is a T1 belong to 0 to and positive T1 is what I want to say. Then I will choose it less than T naught, such that the determinant of Tr of x is positive. Why? Because when you put t equal to 0, what is the determinant? It is determinant of the identity map, which is 1. By continuity of the derivative, continuity of the determinant function here actually as a function of t. Okay, for t some positive number, determinant of the left hand side here, determinant of Rt must be positive. Okay. Now assume that t belongs to 0 to T1. Okay. Now T1 has been chosen in this way. So I say this is good enough. Then put Gt equal to Rt of Bn. See, remember Rt is just some map from Bn to Rn. But we want to say that the interior inside Dn to Rn, but take only the open ball. The open ball goes inside the open ball is what we have to show. So look at Gt equal to Rt of Bn. Okay, we want to show that this Gt is inside Bn first of all. Okay, why Gt is inside Bn? Because t is less than 1. I have chosen to be something, okay, here 0 T1 T1, this one is less than 1. Okay, 1 minus t times x plus, that is the formula, you have to use that. By inverse function theorem, Rt from Bn to Rn is an open mapping. This is very important here. It's an open mapping into the whole of Rn as a map into the whole of Rn. Okay. By step 1, Rt is injective also, because now we are taking T1 to be less than T naught. So both of them will be true here. Okay. So it remains to prove that Gt is equal to whole of Bn. That is the only thing which we need. What so far we have observed is it is injective. Okay, it is an open mapping, and so it is a homeomorphism, diffeomorphism onto GT. So if you show GT is actually Bn, you are done. Okay. Suppose GT is not equal to the whole of Bn. We have already observed that it is inside Bn. Okay. So if some open subset is not the whole space is what? Bn, another open disk, that's all. Then there is a point y which is in the boundary of GT but is inside Bn. Okay. Bn is after all convex thing. So you can take a boundary point, you take a point inside y, inside GT, join them, it will intersect boundary of T somewhere, and that somewhere must be inside Bn already. Therefore, you can have a sequence xn, xk, okay, inside Bn such that Rt of xk tends to y. Okay, because they are elements of GT. Rt of xk will be an element of GT, so they converge to y because y is on the boundary of this set. Passing to a subsequence, if necessary, we can assume that xk itself tends to some point x inside Dn because Dn is compact, right? So, but then Rt of x is the limit of Rt of xk, right? Because Rt is a smooth function actually, so it's continuous also. But Rt of xk is equal to y belongs to GT, because Rt of xk we have assumed that converges to y. The limit is y. So that is an element of GT because it is Rt of something. Okay, GT is what? GT is the image of Rt, so which is an open set. But we chose a point y inside the boundary. That is absurd. Therefore, GT is equal to Bn. So in 2 steps we have proved that we have located a positive number between 0 and 1 such that for all points inside that one, Rt is a diffeomorphism on to the entire Bn to Bn. Okay, now we can conclude the lemma. So step 2 combined with a change of variable formula for integration implies wherever it is diffeomorphism, for all those, this function ft must be the volume of R, volume of the whole thing. Volume of Bn or volume of Dn, they are the same. Okay, so why? Look at this one. This is the determinant of dt is what we have got. What happens to dt if t is inside that interval? This will be an invertible map. Okay, because determinant is positive there. So whenever you have invertible function, diffeomorphism, you have the change of variable formula. Okay, so some deep, not very deep, but some really good analysis has been used here. So volume of ft inside 0 to t1 is volume of the Dn is given by ft, but that's a constant. So what is the meaning of this one? In this non-trivial interval, okay, positive interval, a polynomial function is a constant. Therefore, this ft must be equal to volume of this Dn, okay, on the whole of 0, 1. In fact, if it makes sense on the beyond also, it will be 0. A polynomial which is a constant on some non-empty open interval will be constant everywhere. Okay, so we have computed in particular f0. Okay, f0 is a volume. Now we shall compute f1, then see that it is a different value, and that is a contradiction. Okay, Now look at R1 of x. That is equal to Rx for all points inside Sn minus 1, okay, for all x inside Bn. Therefore, if you look at Rx dot Rx equal to 1, that is the same thing as saying Rx is of unit length, right? This is dot product. Therefore, for any V inside Rn, if you take the derivative of this equation, that is 0, which just means that in any direction, the direction derivative dv of r, okay, denotes direction derivative, dv of r dot rx must be 0. The derivative of this one in the direction of v is nothing but dv of r dot rx plus rx dot dv of rx. That is the Leibniz rule. Okay, and that is 0. So twice that is 0 means this itself is 0. Okay, what does this mean? The entire image under this linear map, see, V is a vector, dr of x operating upon V is the direction derivative. So direction derivatives are all perpendicular to Rx. Therefore, this entire linear space is perpendicular to Rx. It is contained in the hyperplane perpendicular to Rx. But that is of dimension less than n. So this implies the linear map, okay, associated with that as determinant 0. Okay, because its rank is n minus 1 at most. It may be smaller also, I don't care. So this happens for all x inside B. Okay, therefore integral f1 will be 0 because determinant is 0. The right hand side, the integrand itself is 0. Okay, therefore f1 is 0. Okay, f is a constant, f1 must be f0, but on the other side we have volume. Volume of the closed disk or open disk is not 0. So that completes the proof of the statement B for what? Smooth functions. Given any topological space X and a homeomorphism phi from X to Dn, the conclusion of lemma 9.31 is valid for any continuous function g from X to X. Also for we take f equal to phi composite g composite phi inverse where Dn to Dn and apply theorem 9.30. Okay. So what I have done is I have just proved the C1 version here. Now you can apply Weierstrass theorem to get the continuous version. As soon as I prove any one of them, what all the three statements gets proved. In particular, Brouwer's fixed point theorem gets proved. Okay. So that's all. So thank you.